Welcome back, everyone. In the previous video, we have calculated that the partial derivative of the loss with respect to y hat is equal to y hat minus y. Okay, so here y hat is 2 and y is equal to 20. So the gradient is equal to negative 18. So the gradient negative 18 indicates the loss decreases steeply as y hat increases. To minimize the loss, y hat needs to increase significantly. Now, as I promised, let's visualize this, okay? So over here, we have our prediction, y hat is equal to 2. And remember, our target is equal to 20. Now, on the x-axis, you see the predictions. On the y-axis, you see the loss. So what I did essentially over here is how I plotted this. I always like to know when I was watching, tutorials, like how did the instructor get this curve? What I did was I plugged in all the values possible from 0 to 30 into y hat, okay? So 1/2 is given. Y is given, right? That's 20. Y hat is not given. Squared, that's given. So what you can change is, what the y hat values are. So essentially, I took all the possible values from 0 to 30 and I plotted it. And that's how I got this parabola. As you can see, if we plotted it from like 0 to 40, it would go up even more and it would be a nice parabola. But that's not important right now. What's important over here is what you see. This red dot is our prediction, right? The x-axis is the prediction, so this is at 2. And over here, the loss is equal to 162. And remember, we have calculated this before. If we scroll back up, remember, this is how we calculated our initial loss was 162 when our prediction y hat was equal to 2. Okay, so I hope that makes sense. And I'll just scroll back down here. And so that's how we got the initial loss to be 162. So this shows that when y hat is 2, the loss is 162. And this green line over here, you can see, if I zoom in, you see this green line. This is the gradient. This is the partial derivative. It's what we calculated over here. It's the partial derivative of the loss with respect to y hat. As you can see, it's negative 18. And this means the slope or the rate of change at y hat equals 2 is 18. Now, what does that mean? That means that if I increase my prediction by 1 unit, the loss is going to decrease by that 1 unit times the slope, which is negative 18. Now, what does that mean with a numerical example? Well, it means if I increase my prediction from 2 to 3, which is by 1 unit, then my loss is going to decrease by that 1 unit times negative 18. So if I make a prediction, 3, if my prediction was 3, as you can see, my loss decreases to 144, or approximately 144, right? Because gradients use approximation, but let's not hang up on that. Let's say it's almost 144. In this example, it is exactly 144, but remember, gradients are not always, exact to the decimal, but right now it is. Okay, so that means if I increase my prediction by 1, the loss changes by 1 times the gradient or the tangent or the slope of the tangent line, which is negative 18. Okay, and how did we get 144? Well, if you look at your calculator, and 162 minus 18 is 144, which means that the rate of change actually works. So if I increase my prediction by 1, the loss is going to decrease by 18. Now, if I increase my prediction by 2, so I'm at 4, let's see what's the closest I can get to 4. The closest I can get to 4 is over here. As you can see, the loss is 126.8. And if you look at your calculator and you do 162, which is our original loss, and then you subtract 2 times 18 from it, which is 36, you get 126. So the gradient is approximately right over here as well. Now, why did that happen? Well, because the rate of change is approximately 18, okay? So when we increase y hat, our prediction, by 2, so we increase y hat from 2 to 4, the loss is going to decrease by 2 times the gradient, which is negative 18. So increasing your prediction by 2 is going to decrease the loss by 36. So this is pretty amazing, and this helps our neural network give an idea as to, how it should update the weights. Because right now, because of this, we know that, hey, our prediction y hat equals 2 is pretty crappy, because we're really far from the optimal value. And because we calculated this gradient, we know that we need to increase our prediction. What does that mean? Well, that means we're going to propagate the error back to our neural network, and we're going to tell the neural network, hey, our prediction is really low. You're going to have to increase the weights. And now our weights have an idea as to which direction to go. Should we increase or decrease them? And they know that, okay, we need to increase our value. We haven't got to gradient descent, which tells them by how much they should update their value, but at least the weights now know that, hey, the prediction is really low. We need to increase the value, okay? So I hope that makes sense. Now, let's look at another example. Suppose that our prediction y hat is equal to 25. And remember, our target is 20. So over here on the bottom right, you see the red dot. The prediction y hat is 25. And when the prediction is 25, you can see that the loss is 2.5. So in this case, we have overshot, right? Because previously we were over here, and now we have overshot. So now, what happens to the neural network? Well, the neural network knows that, hey, we overshot, and we're going to have to decrease the weights in this case. Okay? And let's see what happens. Over here, the prediction is 25 and the error is 12.5. Now, the slope over here, or the gradient, is 5, okay? So when our prediction is 25, supposedly, let's suppose our prediction was 25, the gradient is 5. That means if we decrease our prediction by 1, then the loss is going to decrease by approximately 5. Now, let's verify that. Right now, the loss is 12.5, and the prediction is 25. At 24, if we reach 24, can we not reach 24? Okay, let's try to zoom in here. If we reach 24, as you can see, we've reached 24. When our prediction is 24, the loss is 7.5. Okay, now what does that mean? Well, that means the gradient again works, because we decreased our prediction by 1. We've decreased it from y hat equals 5 to y hat equals 4 over here. And if we could reach that, we'd see that the value is equal to 7.5. So the loss decreased from 12.5. Remember, the loss over here was 12.5. So the prediction was 25 and the loss was 12.5. And over here, when we decreased the prediction by 1, loss decreased by 5. Why is that? Well, if you look over here, the slope, or the gradient, is 5, which means that a small change in y hat is going to yield a 5 magnitude effect on the loss. Okay? So decreasing the prediction by 1 decreases the loss by 1 times 5. Okay? So we decreased the loss over here from 12.5 to 7.5. So I hope that makes sense as to what happened. And the last scenario is over here. We have y hat equals 20, which is equal to our target, y equals 20. And over here, the gradient, or the slope, is 0. And when that's 0, it indicates that the prediction is perfect and no adjustment is needed. Now, if we come back over here, If y hat, or the prediction, is less than the target, the gradient is negative, right? This is a negative gradient. It's negative 18, indicating the prediction is too low and needs to be increased. Now, in this example, if y hat, the prediction, 25, is greater than 20, or the target, the gradient or the slope is positive. As you can see, it's a positive 5. And this indicates that the prediction is too high and needs to decrease. So I hope you understand why we have to calculate the partial derivative over here. So that's why we have to calculate the partial derivative of the loss with respect to y hat, because it helps backpropagation know, okay, which way do we need to increase the weights? And it's going to tell them, hey, you need to increase the weights. But we don't know by how much and which weight. That's why we're going to use the chain rule, which propagates the error back, and we're going to be able to tell both W1 and W2 by how much they should be increased. So essentially, the gradient provides a clear direction for improvement by showing how the loss changes with respect to y hat. And once this step is computed, it propagates backward through the network, and through gradient descent, the weights will be adjusted. Okay? So I hope this visualization helped you understand the rate of change and what partial derivatives are good for. They tell you how a small increase or decrease in the value, in this example it was y hat, affects the final loss.